Okay, so it's 3 o'clock, welcome to part 2 of our tutorial, where we're going to focus in a little bit more detail on what concretely the internal representation looks like for various JavaScript constructs. So first of all, please feel free to interrupt me with questions if things are unclear or seem just completely wrong. And also, if you cannot hear me, also please, if you want to hear me, that is, feel free to speak up. So let's start. So the basic structure of the IR. It's what you might expect from a traditional compiler. It's a 3-address code structured by the control flow graph, so that the instructions are arranged in basic blocks. Compilers 101, and all of the values are in static single assignment form, meaning every value has one assignment and it would possibly make three nodes. And for those of you who enjoy such things, we built fully pruned SSA, we do it right, and we copy propagations integrated. Fully pruned won't bother you, but with integrated we'll get back to what copy propagation does to your IR. So now from an outline of this part 2, we're going to start with an example piece of JavaScript code to illustrate some of the JavaScript constructs that we all know and love. Well, we know them anyway. Then I'm going to talk a bit about the overview of what the IR looks like, and then dive into a little bit to some of the particularly troublesome features of JavaScript and how those are shoehorned into a traditional compiler IR. Then I'm going to go talk to something I mentioned briefly before, which is constructors. This is how we handle new instructions in JavaScript. Then we're going to talk about why we handle them the way we do and what it is. And then finally, I'm going to talk a little bit about the details of what our source position API looks like. It's integral to our IR. So let's look at this piece of code. This is just things we all know and love. So we have a function, outer. Now note the argument, does this have a laser?
Yeah.
Yes. So note the arguments array. This is a funny way of referring to the argument 0. This is actually a funny way of referring to S. Then this looks like a method call on S. Now we have an inner function, which is simply creating an array and assigning it to the data property. This is an example of how we use constructors. And then down here, we actually call the function outer, it returns some object, and then we look at the data. So now let's just bring up a couple of the issues here. So, things you all know love. Someone had asked earlier about inheritance. So, that's what the prototype chain. I'm going to talk a bit about how we model the prototype chain. This is, as many points said, this has got nothing to do with any notion of a class hierarchy. It's much more mutable. We're going to talk about how we do lexical scoping. This is X is declared out here in function outer. It's now used here in function inner. So it looks like a local variable, but actually it isn't. And I'll talk about how that's modeled. Then we have the arguments array. As I said, this is a funny way of referring to S, and I'll talk about how that's modeled. Method calls, this looks perfectly innocuous, like a harmless little method call. So good, it isn't. We'll talk about what it means to be a method call in JavaScript versus a function call, how we handle that. And then copy propagation, every once in a while, especially for people who are doing things like security at work, they always want to know, well, they all have to ask questions about where a certain high security variable is declared under the control context. And I'm going to talk about what copy propagation does to your IR with this example here, the variable t. Now, the last thing is object creation. This, in fact, is an object creation, right, where we're creating an array of 2 elements. And this is a creation. This is using a JavaScript function as a construct. So we'll talk about how those are handled. And then finally down here, while this looks like a perfectly ordinary reference to a field, property of an object of data, we'll talk about how that is actually made as complex as possible in JavaScript using prototype chains. And I'll talk about how prototype chains are modeled in JavaScript. But first, let's start with an overview of what the IR looks like. So this piece of IR is actually the top level IR of our function. So what do we do? So that's the top level IR of this piece of code here. So it's going to declare the function outer, and then it's going to call the function outer, and then it's going to access the data property of whatever it is that outer returns. So let's see what that looks like. So here's this does just to quickly look at it. Each instruction has an index, and it's organized into basic blocks. Not all numbers are necessarily present, but don't worry about that. That's copy propagation will cause certain ones to be eliminated at times. So this is back to my color coding, this is again a reference. This is going to reference the arguments array. This is constructing an object, and this is referencing the data from it. So that's done. The first thing is we allocate the arguments array. So this looks like a perfectly good. This is how we represent the arguments array in the IR. We just have a new statement within the method that creates an array, and the data flow of the actual argument properties into the array is done by the call graph construction. Next step, we read the function of it. Now, all function creations in JavaScript, all functions are actually constructed from the function object. So this is first we read the global function object. And the next thing is we create the first class function object outer. So this represents the creation of the function outer. Now, remember in JavaScript, functions are first class. They can be passed around, they can be assigned to variables, they can be called, you can do other unspeakable things to them if you want to. And so we represent that, we model that by actually creating an object that represents the outer function. Now, in JavaScript, there are at least 3 different kinds of function creation constructs that all look the same but have rather different meanings. There's a function declaration, a function statement, and a function expression. Now, in this particular case, since this was outer was declared at the top level, it is in fact a function declaration, and what that means is it's actually scoping a global name. Outer is it's a globally visible function. It's a global name. It can be referred to by the name outer anywhere in your code, and that's represented here by an assignment to the global outer object of this value v2. v2 represents the function we created, and our v2 we are assigning that to this global outer name. Now, the next thing is the undefined object is special. Now, why do we use this funny name for it? $undefined. It turns out that people who write JavaScript code, for reasons best known and probably best kept to themselves, decide to override the real name of undefined, and in order to access undefined when we need it, we have to give it a special name. Now we're reading, the next section 6, which we're reading the global function out. And now this, you'll often see this in JavaScript IR, this function, this instruction that does this check. Now, because of the way JavaScript is structured, or actually because of the way it isn't, the way it is in fact not structured, it is highly possible to refer to various local variables that in fact do not exist. You can do things like, you can refer to a global, you can have it that no one has defined yet, and there are certain situations where you get an undefined reference error in JavaScript. Now this is not referring to a property of an object that doesn't exist. That's perfectly fine, and that gives you an undefined object. This gives you an undefined value. When you refer to a local variable or a lexically scoped variable that doesn't exist, you get a reference error. And that's what this check does. You'll often see after global references in the Walla IR or lexical references, you'll see one of these check instructions. And that's meant to model the semantics, that in the cases where the variable wasn't defined or was used in some funny way, you'll get an exception which throws the undefined value. And that's why this ends a basic block, because this may cause control to transmit an exception. Now, the next thing is, this is the global object. Again, this is the way we model all of the global objects in the library, the standard library objects, is such global variables. So this is so that we've seen we saw function here, undefined here. Now this is the global object. Yes, there's a check on the global object, don't ask. And now this is in fact invoking the function outer. You see here we're invoking value v14 is the v14 is read from the global outer, which is in turn assigned from here. So you construct this function, and then we call the function v14. Now, in JavaScript, but this is not Java. This is not the receiver object, as it would be in a Java, like an inverted virtual or an inverted interface. This is actually the function that is being called. So this pointer is also defined. Now, this is not a method call. So in this case, this pointer is v16, which is just the global object. And that's just JavaScript defined. If you can't find anything else to give in this pointer, it just makes it the global object. And then we're also passing the value, this string outer to the pointer. Now, the last thing that happened is when, after we call the function, it returns something, and we try to reference the data property of that. Now, how does that work? So remember in JavaScript, rather there's an object may have a property. But if the object doesn't have the property, the way the semantics such as they are work is that the prototype chain is traversed, and its prototyping objects are also searched for a property with that name. And the way we model that in Walla is we have this we have this IR that reads the prototype value. So v13 is the return value of the call to outer, which is the thing we're trying to read the data property. Prototype values is essentially something like this. For this value, v13, give me all the possible object, this object, and any possible object that might be its prototype. And once you've done that, that goes into v10, and from there, we read the data property of that. So this will give us the data property of the object. The outer return and also the data properties of any prototype object. So again, this is a conservative model. We're not trying to do some analysis to figure out when a particular property might be definitely assigned, so there's no need to reference the prototype chain. It's not doing that. So now, that's a quick overview of the kinds of most of the kinds of IR statements that you're likely to see. Now, please feel free to interrupt me anytime. Yes.
Is this language especially built for JavaScript, or is the same intermediate representation used for Java, or is it mixed?
Yes or no. I mean, it kind of depends. So basically, there was originally an IR for Java. And what we did was we keep some parts are the same. So for example, the new statement that creates a particular type, you see that in Java as well. Some kinds of instructions are related. So the invoke instruction in Walla is actually a hierarchy. There is an notion, it's an abstract notion of an invoke, and then there are specific instructions that are specialized for Java and JavaScript semantics. And then there are other statements like this one, check, which are just specific to JavaScript. It doesn't make sense in Java to try to refer to a local variable that doesn't exist, because the language actually has scope rules. So you're not supposed to do that. And in JavaScript, that's perfectly fine. So we have a special instruction. So it's, in some sense, you can think of it as a family of IRs, where we design it to put as much as possible into a common base. And things like static single assignment form and the control flow graph structure is completely common.
So, Julian, just one other thing along those lines is the core analyses in Walla, say like call graphs and pointer analysis, are the ones inside the Walla core package are built for Java, and then via subclassing and like overriding of, say, the constraint generation, we generate the appropriate constraints for the JavaScript specific instructions. But then the core constraint solving is, reused without modification. So kind of in that manner, the hope is that for other analyses, you could use subclassing to sort of just handle the JavaScript specific stuff and reuse all the machinery for the shared instructions.
So using Rhino, and I think there's a new Ashlarn scripting engine where you can have Java code that posts JavaScript and exposes some of its objects. Is Walla capable of modeling that?
Sorry, JavaScript code that does what?
Java code that posts JavaScript and exposes some objects such that can be referenced from the JavaScript.
Well, you can do that in Rhino, and no, there's no. At the moment, if you wanted to do that, you would have to essentially craft models for what the JavaScript code does. In theory, you could certainly analyze both and try to stitch the IRs together. There is currently no support.
You haven't done that yet.
There's
no reason.
You'd have both languages in compatible IRs. If you would then, what doesn't exist is any logic that understands how to wire them together.
Okay, that makes sense to me.
All right, so this is a quick walk through what some IR instructions do. Now let's look at some specific JavaScript features. Now we're going to go back quickly to the example. Now what the outer function did was, again, it has an arguments array, refers to undefined, everybody does that. Now if you remember, there was a local variable called x, which was lexically scoped. Now, the way we effectively represent that is you'll see these things: lexical this, lexical that. And you'll see uses and definitions of variables with this name. They look a lot like globals. I'll talk about how we do that. This is, again, we're constructing the inner function here. We are then referring, this is a first-class field reference. Basically, the previous example, we saw accessing the data property that had a fixed name. But here, the property name is actually a value. And now, down here, we have a second kind of invoke. I remember I told you that we were doing x.index of, and that looks like a method call. But method calls are funny. And so this is a different kind of invoke that handles method calls. I'll talk about that.
Sorry. I was trying to move the mouse off the code.
Thank you. And then this is an example of something that's completely common. We're doing a greater than operation here. Again, greater than is not so different from in Java or anywhere else. So and a conditional branch again is the same. And now here, finally, this is where we construct another object, and I will talk about how that construction is modeled. So in particular, we have a similar thing for our inner IR. I'll get back to this. Basically, the things to note here, again, we have the arguments array and stuff. Here's an example of using lexical. And note that even though we're in the inner IR, sometime I'll figure out how to push the right button here, excuse me. Even though we're in the inner IR, in this case, we know we're referring to the lexical variable x that was defined in the function outer. I'll talk about how that's handled as well. And here is the example of copy propagation. Remember, there was this variable, there's a variable called t, which has been completely removed and simply replaced by the copy string. So I'll talk about that again also, and then so. Now, hopefully, this is the only slide, I think, where I risk straining anybody's eyes. I apologize for this blue color. We're going to talk about prototype chain, which is what JavaScript does for inheritance. We're going to talk about method calls and why they look perfectly innocuous like Java, but they're not, and I'll talk about that. And then talk about object creation, and these two are linked together because we effectively treat object creation as a kind of method call, as Manu alluded to. I'll talk about lexical scoping, all the fun you can have with the arguments array, and then finally copy propagation, which isn't a specifically JavaScript issue, but Java source frontend also does copy propagation with the same kinds of results, but it's often the case where people are doing analysis at in JavaScript, they see the source code, they see a variable t, and they say, well, but I want to find the declaration of t for some reason. This is why this makes sense. All right, so the prototype chain. So JavaScript uses prototype-based inheritance. Basically, every object has a prototype. And objects. Prototype and properties can be found in the prototype. So when I say x.data, if x doesn't have data, I see this prototype does, and so on. Back. And what we are doing is a lot of the analysis, especially the float construction and pointer analysis that we do in JavaScript, is float insensitive. And what that means in this case is that we do a conservative model of inheritance, and we have no models for an object that a property data must have been defined, so you don't need to look for prototype. We conservatively gather all prototypes and conservatively look at any data field in any of those prototypes. So let's look at that's how this works. So the way we're keeping track of this in the analysis is we have an abstraction called prototype values. So for example, object, which is the base type, not really a type, it's something in JavaScript. There's an object, it has a prototype. Now function, the global function object has its own function prototype object, but that prototype object in turn has object as its prototype. So the prototype values for function will be both. Now, in JavaScript, array is a function to us, but basically the array prototype object has the function object as its prototype, and so its prototype values, the prototype values for array is going to be all three. And now if I create v4 here, I make a new array, it again has its own prototype, but it inherits the three that array had. And so this is what, and so when you see prototype values, this is what you'll actually see in the pointer analysis. You'll see transitively my prototype and every prototype, any object, any prototype of me might have. So now handling calls. Now let's look at JavaScript has both method and function but I can say f of 3, which basically looks like a perfectly ordinary function call f, give it the 3. And I have a.m3, which looks like a method. Now, JavaScript doesn't actually have methods, right? Objects can have functions as properties. And there are a bunch of rules that tell it in which it decides very locally when a particular function call should be given a particular object to prototype. In this case, essentially, it says the rule says you see a.m. That means the function call m, or the property m, is going to get the function, the object a, as it's this pointer. This is a method call. But this is going to call exactly the same function, right? F equals a.m. It looks like the same code. But in this case, because syntactically there's no dot, it's going to decide that this is a function call, not a method. And as a result, the function in this case will not get to this pointer, or it will get to the usual the global object as this one. So those are two different kinds of invokes. You might think those two calls should do the same thing, but of course they don't. Now, in our case, and I'll talk about this not on the next slide, but just after that, we actually have a third kind of thing that looks a lot like a method call, which is the new expression in JavaScript. So Voila actually has three different kinds of them. So let's just look at those. We're going to look at the first two. Now, handling calls. So the key difference is the following. So if we look at this, let's say we have this as.index of O. What you'll see in the Voila IR is this thing from the example from the outer function here, this dispatch in, dispatch of v20. So we're calling, it says, this means call whatever function is denoted by v20 on the object v3. So in this case, v3 is the receiver, and v20 here is not the function, it's the name of the function. So that's illustrated here. So if I have v3, it potentially points to two objects here, and each of those has an index of property. So what this is going to be doing is it's going to figure out whatever function this is, it's going to invoke it on this object. Now, the reason, so you might think you don't really need this in your IR, right? You could just model it as read the property, call it within this one. And that's what we did at first. Now, there's a nasty issue if you do that, which is if you look at this, suppose I had suppose S, the model of S, is imprecise. I have two different abstract objects that S could represent S. If each of those has a different index of function, if I simply model it as reading the property and then a separate invoke, I'm actually going to get an imprecise model of this point. I'm going to think that either function could be invoked on either abstract object, which is actually not the case. So that is what this dispatch pointer does. This is essentially doing a double level of indirection. It says for each possible abstract object of v3, look up each for that abstract object. Look at its model of index of. Call those functions on only that abstract object. And that's as opposed to down here, where if I do s.index of, and then I call f of o, what I'm going to get is I'm going to read the prototype values of s, and then going to I'm then going to call, I'm then going to check, I'm going to get all the possible prototypes of anything of all the abstract objects of v3. I'm going to get all their possible index objs, and then I'm going to do that. So that's why we have two different kinds of invokes. So we model things that look like method calls and things that don't look like method calls. Different. Now, does that make any sense? Feel free to ask questions if it doesn't, Andy.
Question regarding the previous comment you made about how you the possibility of two different indexes being called two different possible objects. If the index of were modeled as just a property of the object, then wouldn't each of those two distinct objects potentially have wouldn't the values that were assigned to their index of properties be distinct? And so if you knew which of the objects you yeah, the context sets them to know which object you were referring to at the point where you see the index of it, you know which index of it is.
No, the reason that this is difficult is that is difficult is that I have no idea how to use this return. No, that's one reason. Other reasons. So the trouble is that in Java, for instance, when I have s dot index of, index of is a property of s. There's one object which has a method. In JavaScript, s is an object. Index of is a different object.
Sure.
So if I have two different s's, each of which has a different index of, I now have a correlation. I need to make sure that I only call the right index of on the right s. So I get two possible ways of calling instead of four, which would be the case if I model it like this. I think the key distinction with Java is that there are two objects floating around here, not one, because JavaScript has first-class functions, and Java does not. No, Java does not yet, anyway, at least not really. Well, I'm sure they're working on it. Just waiting for Java. All right, so now, did that? I think so. Okay. May have clarified things to the extent to which people care about it. Okay, so now I was mentioning that there were a couple of people asked questions earlier saying, why do you need a method call for new? Now let's go. So what does object creation look like? Again, it looks like perfectly innocuous if a new statement is very similar to the new expression in Java, but it's not. And the key distinction is in Java, X here is a type name. It's a static constant. You aren't allowed to mess with it. In JavaScript, it's an expression. The way that shows up, like for example, here's the variable X. Based on some random condition, I'm either going to reference the global object or the global array. I'm going to assign that to X, and I'm going to make a new one of whichever of those I chose, and I'm going to pass it the argument 5. Now, what does that mean? So that already we have a dynamic. So we have dynamic semantics, and then we don't know statically what X is. So we don't know what it is we're creating. And then that is already starting to smell a lot like that. But it gets worse. I mean, I was going to say, or better depending on your perspective, but no, I think it just works. New has also very diverse semantics. So let's look. This looks kind of weird, right? I'm either creating an object or an array, depending on some random condition. But it gets worse, because now if I have an object, if I give it no arguments, the meaning of that is return a fresh object, which seems like something surprisingly easy for JavaScript. However, suppose I give it the argument 5. Now it returns 5. What a copy of 5. That's 5. Why? Don't ask. I don't know. I'm just working it. Now, let's say I create an array. Suppose I pass the argument 3. Now it creates an array of size 3. Again, this seems something reasonably logical. What if I pass 3, 2? Now it returns an array of size 2 with the elements 3 and 2. So depending on how many arguments I give it, the meaning changes completely. So now we have a dispatch both on the type of thing that I'm getting and also the number of arguments. And so now what we have, the way we model that is we essentially treat new as a special kind of function. And I will get into, I'll show you some examples a bit later about what we do. We basically, for each case of each kind of thing that's legal to call new on, we go through, we figure out what the JavaScript model says we're supposed to do, and we generate some synthetic IR to simulate that. So what does this look like? So we model new as a dynamic dispatch, we translate it to a special method call. So for example, this new inner S from the outer piece of code, what it actually looks like is this. First, you find function, and then you construct the function inner. This is creating the first class function inner. So then when you call new inner, you get V8 here, right? You're calling new effectively on inner. So basically construct here is the way our IR is printed when it's using a new statement, essentially a method call, a function call that's actually doing a new. And it's passing the odd value 3 because 3 is S. So I'll show you, so what does this do, right? This isn't calling the function inner. at least, well, it is, but not in the normal way. And so I'll show you the IR, the target method for this construct called generated, and I'll show you some examples in a few slides about what those actually are. Now, let's go. So again, well, in Java, I can write X in an outer scope. I can have some inner classes, and I can write X. But in Java, that X in the inside is read-only, and in fact, the X on the outside has to be final. So what that means is what actually happens in the translation of the compiler is it gets turned into various function parameters and constructor parameters, and it's all compiled away. In JavaScript, we don't have that freedom because it's read and write support, and we also allow, for those of you to whom the phrase upward funarg is not, if it's a meaningless buzzword, if it's just a meaningless couple of nouns, ignore it. If it's not, JavaScript does allow those. And so the way we deal with all of that is we effectively model lexically scoped variables as heap locations. And so our reads and writes are flow insensitive, and we are not doing SSA renaming on that. So when you see our local, I said we convert local variables to SSA, and we do, but lexically scoped locals are special and do not. They effectively get treated like heap locations. So for example, here in the outer method, you'll see things when you see the variable x, we have a couple of assignments to x outside, and down here we have a read of x. And essentially you can see, right, lexical x at outer is effectively going to be treated like a heap location, so you'll get the obvious conservative data flow to the read. Now, this is an example of where you need a check instruction in JavaScript. In JavaScript, it is possible to arrange things in such a way that you try to use x when you've never done anything to it yet. And in that case, this is one of the few cases that the JavaScript language actually defines as an error. It's extremely rare. Usually, JavaScript's philosophy is do something. It doesn't necessarily matter what, just keep going. But in this particular case, it's going to throw a reference error. So you're trying to use a variable you haven't even created yet. So I'm going to give you an exception. And again,
So, question about choice of representation.
Yes.
And this may speak to my ignorance of
all
this kind of languages, but so you represent all of your functions in your IR as classes with a special named function inside. So wouldn't it be possible to represent lexically scoped variables as members of those classes and just do like a filter conversion thing to make sure they all have the right values that they're needed?
We have experimented with different ways of representing lexical scoped variables. At one point, we had a rather complex mechanism that actually tried to do SSA conversion all the way down to rewriting the IR when it discovered new lexical definitions. That was used to support a particular application, but it created a bunch of disadvantages and became extremely complex. What we have now is sort of on the other extreme to trying to be relatively straightforward and not worrying too much about this. It's a little hairy when you start converting things. It's a little hairy when you're handling mutable variables, and it gets a little bit hairy. And one of the particularly weird things is that, well, JavaScript is a single-threaded language, and it will tell you that. The way it is actually used in web browsers, that it starts to push the boundaries of that in funny ways. So we are trying to aim for something relatively simple to get right.
And the IR you're representing was designed for Java. The IR you're representing is originally designed for Java. So yeah, handling applications that are some of the things sort of pointer to a thing in the IR that represents Java.
You do not have that experience. Now. So that was lexical scope. Now, another thing that we all know and love is the arguments array. So basically, what does this mean? JavaScript reifies its arguments in an array, which allows array indexed accesses to all parameters, and it allows accesses to unnamed parameters. So in Java, function. You may have declared it with 2 or 3 arguments, A, B, and C, but you can pass any number of arguments to the call site if you want to, parameters, and so the ones that you pass that correspond to named arguments get bound to those names. Other things just kind of get swept up into this arguments array that allows you to access. And we basically model that with an explicit array creation, argument is assigned to a new array, and all of the accesses look like normal array accesses. For us, we just model that as normal array access, and the pointer analysis during call construction is responsible for making sure that the data from the parameter values flows into the array. And for those, and there are, so you can say, well, now what we've done here is, since our model of arrays does not distinguish specific indices, if you use the array argument, arrays arguments where you'll get all of your arguments are going to flow together and it's going to be precise. We have AST rewriting support and IR rewriting support that allows you to break that out in cases where everything inside is a constant. But I'm not going to get into that right now. So basically it looks like this. You just have I create the array and I just have ordinary looking accesses to it. And yes, things left to its own devices, and that is going to cause you some imprecision in cases where the argument array is constants, and you know the particular call cycle the value is. Now, the last JavaScript specific thing I'm planning to tell you about is copy propagation. Well, this isn't really JavaScript specific, this is more SSA specific. So for those of you who know SSA conversion, every variable is given one assignment, things that have multiple locally written to use fee nodes. Now, and they've been and for a long time, people have integrated copy propagation into SSA, meaning that if I have an argument, if I have a value whose only assignment, whose only value is just assigned from another value, I don't even need to keep track of it. I can just delete it and use the SSA value off the right-hand side. And that's what we do. It simplifies later analyses, and it means that if you are writing an analysis in Walla, you are never going to see an assignment statement. We do not have an assignment statement in our file. That's one of the advantages. That's the main advantage you get. It's just one case that you never have to do. Now, I'm not going to get into this in detail, but for situations like in security analysis where you're looking at, I want to know the control flow context of a particular assignment statement. Basically what I'm saying there is that SSA is being too coarse, and you actually want separate values for the same data flow value in different control flow contexts. And that, the traditional way of doing it in SSA form is to introduce these things called high nodes. And Walla, separately, we will do copy propagation, but separately, there's support for introducing pi nodes in Walla, and I'm not going to get into it here. There is a piece of code called the pi node call graph test in the call graph tests package, which illustrates how this is used. It illustrates it in the context of Java, but basically the same support can be used in JavaScript. You can write, there's something called a pi node policy. You can basically say, for example, if you have high security values, you can say that you want to distinguish control flow contexts. And this is just how that works. So let's say, initially, let's say we had this. Here's the IR from outer. Now, inner rather. So let's assume that initially you created this value v10, which represents v7 represents t, and you assigned it the constant suffix, and you were using t down here originally. What copy propagation does is it realizes that 7 is completely unnecessary, and it simply substitutes v10. And if you wanted this to come back, you could attempt to use a pi node that distinguished v7 between the different control flow contexts and know that these are different things. All right. So that was the IR of the bit of example code I gave you. One of the things I had said was describing how we translate use statements. I had argued that they were a lot like dynamic dispatches. And what we do is we generate these function calls to special method bodies that we make up now. I'm not going to go through all the different ways that we make them up because there's one for each case in my JavaScript semantics. Semantics is maybe being a little bit charitable from JavaScript spec, and I'm going to illustrate a couple of examples. So they're designed. Each of these is designed to model the semantics of new. It models the semantics of new, each one in a specific case. It generates synthetic IR, and you generate constructors for each case, so different types and different parameter counts. As I was showing you with the four examples of object and array, both of these can radically change the meaning, and I'm going to illustrate that. So the first one is when somebody calls an array with 0 arguments. What that actually means, the semantics, is to create a 0-length array, which kind of makes sense. It's one of the cases that seems to make sense. So what do we do? The first thing is we create a new array object here, and we copy the prototype to the new object. Remember, we create a new object, and so with the semantics tell you make a copy, and you set up the prototype pointer. We then set the length to 0, and this is a case where we actually know the name of the field we're writing. So it looks like a static field reference. We're assigning 0 to the length. And then we return it at the end. We return the object. So that's one example. The other example is, you notice there was a call to new inner of S in my example. And so what that's doing is it's using a function as a constructor. And the way the semantics of JavaScript defines that is you create a new object, and then you copy inner's prototype, set up the links so that inner's prototype is the prototype of this new object. You then call inner with the new object as this one. This is basically reading the ECMAScript spec and doing the steps. Monkey see, monkey having written the spec in the first place, I suspect too. Now, so you called new, and now, this is weird. This is quite bizarre. We have two return statements. So what's going on? Two things are going on. The semantics of JavaScript say you return the result of inner if it's not null. If it is null, you return the new object you create. And the way that is modeled here is so V8 is the result of the invoke, and V6 is the object we created. So we capture, these are the two cases, you return either way. Now, this looks completely wrong. It looks like this piece of code here is dead, because it's a one return statement followed by another. But here, this is an approximation. We're relying on the fact that we're doing it with flow-insensitive analysis. So things like pointer analysis is simply going to see both return statements, and it's going to approximate the different return statements. So this is how we capture the semantics of JavaScript, which is you just do this. And it's just simpler to generate the synthetic IR without the condition. So that's what we're doing. All right, so that's what the constructors do. And that's two examples now we have for arrays with one argument, arrays with different numbers of arguments. We have function, you can create strings, you can create an object with different multiple kinds of objects, you can do date, you can do regex, you can do all kinds of weird, horrible things. And there are a series, and we have there's a function JavaScript construct target selector that synthesizes an IR analogous to this.
Are there other places in which you build the intermediate representation using the fact you're doing a flow-insensitive analysis, or is this the only place?
No. Well, for instance, the way we are currently modeling lexically scope variables does not hurt us greatly when we're doing things in the flow-insensitive. Would hurt us more if you would have to do something more elaborate with lexically scaled variables if you wanted to handle it, if you wanted to do it in a more sensitive way.
I think there the IR allows for a flow-sensitive treatment.
Yeah.
It's just that our call graph construction doesn't do it. I think the other place would be with the get prototype instruction, though, that you mentioned before.
Right. So the prototype, we basically the way the prototype values operation in the IR is the way we interpret that is transitively all possible prototypes of this object. So, in particular, in cases where you're doing inheritance in JavaScript, and for example, if the prototype has a property, and then a subtype has the same property, those are going to flow together because we're being flow insensitive. The main reason, in Java you couldn't possibly do that, right? You basically said you don't have an inheritance. You can't do that in Java, right? Because inheritance is the other thing you have. In JavaScript, it's not as common to do that because more idioms involved in passing first-class return. So now, Manu was saying that at least with Rhino, we keep very precise source information. So let me just this is just to give you a quick flavor of some of the APIs for that. So we preserve source location, as Manu said. We preserve two things. One, variable names. So if I have a variable S or T or whatever else, when we do SSA conversion, the names of the values are recorded. We allow you to get hold of those. And IR instruction source locations are available from the IR as well. The information depends on the front end in terms of how precisely we can map instructions back to the source code. But it's worth noting that for all of the front ends we have, the mapping is much more precise than it's possible to express, for example, with Java bytecode. The bytecode format only allows you to express line numbers. That's all the JavaScript spec. The Java spec, but for JavaScript we have much more precise information in all the front ends we have. What I'm going to tell you is based on what we currently get from Rhino 1.7.3. Now, let me go back to the inner example. Let's say we have the following instruct. You may notice if you dump IR in Walla, you get a bunch of information, you get a sort of representation of what the instruction is. For example, in this case, it is a field ref. But you also get a bunch of source mapping information by printed afterwards. In particular, in this case, you get told it's in tutorial example.js. It's character offsets 142 through 154, which is line 7. And in this, at this point in the code, value 11 represents the value array, variable array, and value 3 represents the variable. Now, the way this is computed when we dump the IR is the following. That's if you have an IR, we have a couple of instructions you can ask. You can get the local map, and this is where SSA is recording the source names that correspond to SSA value numbers. Basically, you say get local names. You give it a program counter, which is your offset in the instruction array, and a value number, which is the value you care about. For example, in this case, 3. You could put 3 here. If you did this, you'd get back this array containing 1, that straight 1. Now, the reason this is an array is due to SSA and due to copy propagation. You can have cases where the same value number actually denotes multiple variables. For example, when you do copy propagation with T, if T had been assigned to another variable, this array would have multiple names. Now, to get positions, there are two things you can do. A method itself has a source position, and you can also ask for the source position of a particular instruction index, which again is this offset in instruction. So both of these two things return you a position object. Position object has an API like this. You can ask for the first line, the last line, the first column, the last column, the first offset, the last offset, the URL, which is effectively the file name. But in JavaScript, right, a lot of things aren't from a local file. They're just an arbitrary URL. So that's what you get here. In Java, in many cases, this would simply be file / whatever. But it could be an arbitrary instance of P as well. And then you can also do this, you can ask for the input stream. So when we are parsing source code, Lava keeps enough information to be able to reconstruct whatever stream it was from which the text came. So if you wanted to get the exact source text that corresponds to a particular argument, a particular instruction, you could ask for the first and last offset, which are character offsets in the file. You could get the input stream, and you could read those characters. Literally reconstruct portions, you have enough information to reconstruct arbitrary portions of the And not all of these are defined by everything. So first line is pretty commonly, everybody has that. Last line, Rhino actually doesn't have. You need to count new lines in your source string to figure out what the last lines. Rhino actually makes this fairly painful to compute. Columns, Rhino does not actually give you columns. Some parsers, the internal IBM parser in JavaScript, actually keep track of line and column. Offset is more common. Eclipse, for example, gives you the offsets, character offsets in the file. URL is everybody has that. One thing to note is that first and last offset are a little bit weird. They're actually character offsets. And so if you are using, for example, a file, an operating system that has some strange idea, like a new line is actually 2 characters, the offsets can get slightly weird. So if you see that you might see output on Linux and see output on Windows, and there are character offsets might actually. But that is what allows you to get the right thing from the input stream. All right, and that is sort of a whirlwind tour of various aspects of how we attempt to model portions of JavaScript in Walla and how we reflect the information that we preserve from the front end into